In this video, we will be discussing certain properties and some fundamental theorems related to the basis for a vector space, which are essential in the understanding of vector spaces and the applications that build on them. Especially, we will be dealing with finite dimensional vector spaces, and these properties and theorems reveal the subtle interrelationships among the concepts of linear independence, spanning sets, bases, and dimension. Theorem 1. Uniqueness of basis representations. A non-empty subset S of a finite dimensional vector space S is a basis for V if and only if every vector in V can be expressed as a linear combination of the vectors of S in a unique way. So it says that the subset S is a basis if and only if any vector can be expressed as a linear combination in a unique way. So the spanning will be unique. So already we know that S is a basis if it is linearly independent and spans. So the theorem says that if it is a linear basis, then the representation will be unique. So the proof goes like this. So let us assume that S is a basis where S is equal to set V1, V2, etc. Vn. So S is linearly independent and it spans V. Suppose there are two representations for a vector V in the space. Say V equal to C1 V1 plus etc. plus Cn Vn and V equal to K1 V1 plus etc. plus Kn Vn. So we have to prove that the representation is unique, which means C1 equal to K1 etc. Cn equal to Kn. So from this we will get C1 V1 plus etc. plus Cn Vn plus minus of K1 V1 plus etc. plus Kn Vn equal to V plus minus V equal to 0. So that means sigma Ci minus Ki Vi is equal to 0. But each of the Vi's, say the set V1, V2, etc. Vn is linearly independent, and therefore the 0 combination is the trivial combination. So Ci minus Ki equal to 0 for each I, which means C1 equal to K1, C2 equal to K2, etc. Cn equal to Kn, and therefore the representation is unique. Conversely, assume that any element of V is a unique linear combination of vectors of S. So immediately it means S spans V. Now it is enough to prove that the elements of S are linearly independent. So consider C1 V1 plus etc. plus Cn Vn equal to 0. But the vector 0 also has the representation 0 V1 plus etc. plus 0 Vn, and the representation being unique, each Ci equal to 0, and therefore S is linearly independent and hence is a basis for V. Theorem 2. Let V be a finite dimensional vector space and let S is equal to V1, V2, etc. Vn be any basis. Then any subset of V containing more than n vectors is linearly independent, and if a subset of V has fewer than n vectors, then it cannot span V. So the theorem says that no set of vectors containing more than dimension of n vectors can be linearly independent, and any set which contains less than n vectors can span V. So the number of elements, the maximum number of elements of a linearly independent subset is n, and the minimum number of elements in a spanning subset is n. So given S is equal to V1, V2, etc. Vn is a basis for V, then S is linearly independent and spans V. So we will prove that if there is a subset of V containing more than n vectors, then it is linearly dependent. So let W equal to W1, etc. Wm be a subset of V with m greater than n. Then we will prove that, so it is linearly dependent. So we will prove that there is a non-trivial linear combination which is equal to 0. Since v1, v2, etc. vn spans v, so each of the vectors of v can be represented in a unique way as a linear combination of S, because it is a basis 2. Hence, each of the wi can be expressed as a unique linear combination of vi as wi equal to sigma j from 1 to n aij vj for I equal to 1 to m. So we have a system of m linear equations in n unknowns. Note that the system is not homogeneous. Now let us consider k1 w1 plus etc. plus km wm equal to 0. Now that means sigma ki wi equal to 0. So inserting for wi from equation number 1, sigma I from 1 to m ki, sigma j from 1 to n aij vj equal to 0. So we can interchange the summation and these vectors and scalars, because some of them are independent of the indices. Therefore, we will get sigma j from 1 to n, sigma I from 1 to m, aij ki into vj equal to 0. So, expanding this, we will get sigma I from 1 to m, a1j, I mean ai1 k1 v1 etc. Okay, so we have this expanded form of this summations in this equation. So we will get like this. We have a linear combination of the vectors v1, v2, etc. vn, which is equal to 0. So we will get a11 k1 plus etc. plus am1 km into v1 plus etc. plus a1 and k1 plus etc. plus am and km into vn equal to 0. But v1, v2, etc. vn is linearly independent, and therefore each of the coefficient is 0. Hence we have a system of homogeneous equations. Note that we have a system of n equations in m unknowns, and the number of unknowns is more than the number of equations. Therefore it has non-trivial solutions. So the unknowns are k1, k2, etc. km. Therefore there exists some ki different from 0 satisfying this set of equations, which means there exist vectors, scalars k1, k2, etc. km, not all 0, such that sigma ki wi equal to 0. Therefore the set w1 wm is linearly dependent. So the conclusion is no linearly independent set can contain more than dimension of v elements, because we have already defined dimension of v as the number of elements in a basis. The second part is, let us consider a subset of v containing less than n vectors. We will prove that it cannot span v. Suppose it spans v. Then any element of v is a linear combination of the vectors in W. In particular, v1 is an element of v. Therefore, v1 can be expressed as a linear combination of the vectors of W. Therefore, there are scalars alpha 1 etc. alpha m, such that v1 equal to alpha 1 w1 plus etc. plus alpha m wm. And v1 is a basis element, therefore it is different from 0, because we know that any set containing the 0 vector is linearly dependent. And hence, it being different from 0, there is at least one k alpha k which is different from 0. So without loss of generality, let us assume alpha 1 is different from 0. Therefore, we can express w1 as 1 by alpha 1 v1 minus 1 by alpha 1 into alpha 2 w2 minus etc. 1 by alpha 1 into alpha m wm. That is, w1 is a linear combination of v1, w2, w3, etc. wm. Therefore, span of w1, etc. wm is equal to span of v1, w2, etc. wm. But by assumption, w1 etc. wm spans v. Therefore, the conclusion is span of v1, w2 etc. wm is v. Okay. Hence, let us consider the vector v2 in V. Since v1, w2, etc. wn spans v, v2 is a linear combination of these vectors, and by the same argument, as it is different from 0, there will be at least one of the scalars or coefficient different from 0. So we can express v as a spanning set of v1, v2, w3, etc. wm. Okay, so continue the argument in, say, m is less than n. So if you continue the argument in m steps, we have a span of v1, v2, etc. vm is equal to v. But m is less than n, therefore the remaining vectors in the basis vm plus 1, vm plus 2, etc. vn, okay, can be expressed as a linear combination of v1, v2, etc. vm, which is a contradiction because v1, v2, etc. vn are linearly independent. Therefore, S cannot span V, which means no subset of V containing fewer than the number of basis elements can span V. Third theorem, all bases for a finite dimensional vector space have the same number of vectors. And this theorem makes sense in defining the dimension as the number of elements of any basis. Any basis we have defined as the number of elements in a basis, and which is based on this particular theorem. That is, there cannot be two different bases having two different number of vectors. So if you choose any vector, any basis for a given vector space, the number of elements will be always the same, and hence we define the dimension as the number of elements in a basis, which we have already done. So let us consider two bases, say S1 and S2, having n and m vectors. So say S1 equal to V1, etc. Vn, and S2 equal to W1, W2, etc. Wm. Now S2 is linearly independent, and therefore it cannot contain more than n vectors because S1 is a basis. Therefore m less than or equal to n. By the same argument, S1 is linearly independent, and choosing S2 as a basis, it cannot contain more than m vectors. So n will be less than or equal to m. So from these two inequalities, we have m equal to n. Theorem 4, plus minus theorem. It says that let S be a non-empty subset of a vector space V if S is linearly independent and if V is a vector which is outside the subspace spanned by S, that is, which is not in the subspace spanned by S, then by adjoining V to S, the set S union singleton V is linearly independent. And if a vector V in S is a linear combination of the other vectors in S, then span of S minus V is equal to span of S. Okay, so the theorem says that if you choose a spanning if you choose a set and you take a vector which is not in the spanning of the given set, and if the set is linearly independent, by adjoining the new vector to the set will not affect its linear independence. And similarly, removing a vector which is a linear combination of the remaining vectors does not affect the spanning set. So proof goes like this. Let S is equal to set V1, V2, etc. Vm. So A part, we assume S is linearly independent and choose a vector V not in span of S. So we have to prove that it is linearly independent. So consider C1 V1 plus etc. plus Cm Vm plus BV equal to 0. We have to prove that each of the coefficients are zeros. So we will claim that B equal to 0. If B is different from 0, then V is the linear combination minus C1 by B into V1 plus etc. plus minus Cm by B into Vm, which means V1, V2, etc. Vm spans V, which is not correct. Therefore, B must be equal to 0, which reduces equation number 1 into C1 V1 plus etc. plus Cm Vm equal to 0. And being linearly independent, each of the coefficients are zeros. So, C1 V1 plus etc. plus Cm Vm plus Bv equal to 0 implies each of the coefficients are zeros. Therefore, it is linearly independent. Therefore, S union singleton V is linearly independent. And for part B, let us assume V is a vector in S. We suppose that V is a linear combination of the other vectors in S. So without loss of generality, let us assume that V equal to Vm. You can choose any vector. Then there exists scalar C1, C2, etc. Cm minus 1 such that V equal to Vm is equal to the linear combination of the other vectors V1, etc. Vm minus 1. Now, removing V from S, you have S minus V, which is equal to S minus Vm. Sorry, there is an error. It must be Vm, not Vr. It is a subset of S. So span of S minus singleton V, subset of span of S. Now, the other inclusion or proves the part of the theorem. Let W belongs to span of S. Okay, then there are scalars alpha 1 etc. alpha m such that W equal to sigma alpha I Vi. But Vm is a linear combination of V1 etc. Vm minus 1, which reduces W as a linear combination of V1, V2 etc. Vm minus 1. Therefore, W belongs to span of S minus V. That is, any element of span S is in span of S minus V. That means span of S is a subset of span of S minus V. So, from 2 and 3, we get span of S minus V is equal to span of S, and hence the proof. So, it says that the removal of a vector, which is a linear combination of the remaining vectors, does not affect the spanning set. Theorem 5 is, let V be an n-dimensional vector space and let S be a subset of V with exactly n vectors. Then S is a basis for V if and only if either S spans V or S is linearly independent. So, given a set of n vectors where n is the dimension of V, it is enough to prove that either S is linearly independent or S spans V to say that S is a basis. So proof goes like this: given dimension of V is equal to n. Therefore, by the previous theorem, any basis has exactly n vectors. So let us assume S subset of V has exactly n vectors. Suppose S is equal to V1, V2, etc. Vn. So suppose S spans V. Then we will prove that it's a basis. For that, it is enough to prove that it is linearly independent. So we see what happens if S is not linearly independent. If it is not linearly independent, there are scalars C1 etc. Cn not all 0 such that C1 V1 plus etc. plus Cn Vn equal to 0. So suppose Ck is different from 0. Then Vk is a linear combination of the other vectors in S. Hence, by removal of Vk from S, span of S minus Vk and span of S are the same. That means span of S minus Vk is V itself, because span of S is V. So we get a set of n minus 1 vectors spans V, which is not true because the dimension of V is n. Therefore, we have a contradiction, so the assumption goes wrong. Okay, therefore S is linearly independent and hence is a basis. Conversely, assume S is not conversely. So now we assume S is linearly independent. So it is enough to prove that S spans V. Suppose span of S is different from V. So there is a vector which is outside span of S and in V. So we will adjoin that vector to S. Then S union singleton V, if V is that particular vector, then it is linearly independent. This is again wrong because we have a set of n plus 1 vectors now which is linearly independent in V, where the dimension of V is n. So this cannot happen. Therefore, the assumption is again wrong. Okay. Theorem 6 is, let S be a finite dimensional subset of a let S be a finite subset of a finite dimensional vector space V. Then if S spans V and not a basis for V, then you can reduce S to a basis by removing some vectors, some appropriate vectors from S. And if S is linearly independent but not a basis, then it can be extended to a basis by inserting certain appropriate vectors into S. So let us assume dimension of V is n and S contains m vectors. For part A, suppose S spans V and is not a basis. Okay, since S spans V, the number of vectors in S can be either equal to n or greater than n. So m is greater than or equal to n. Since S is not a basis, it already spans, therefore it is not linearly independent, which means it is linearly dependent, and there is a vector in S, say W1, which is a linear combination of the other vectors. Then S minus W1 also spans V, because S minus W1, span of S minus W1 is span of S. So suppose S1 is S minus singleton W1. If S1 is linearly independent, this is a basis for V. If S1 is not, already it spans V. So by the same argument as above, S2 is equal to S1 minus singleton W2 spans V. If S2 is a basis, then we are done. Otherwise, we continue the argument for a finite number of steps, say exactly m minus n times. Okay, then we get a set Sk, which is equal to S minus W1, W2, etc. Wk, which is a basis for V. So we have reduced S to a basis for V by the removal of appropriate vectors from S. Now for part B, assume S is linearly independent and is not a basis for V. Therefore, the number of vectors in S is less than n or less than or equal to n. Since S is not a basis, it does not span V. Therefore, there is a vector which is not in V. Say, which is not in the, not in V, which is, there is a vector W1 in V which is not in span of S. So there is another error I have written which is not in span S. So you have to change it. Then the set S1 equal to S union singleton W1 is linearly independent in V. If the span of S1 is V, then S1 is a basis. Otherwise, there is another vector W2 which is not in the span, so that S2 is equal to S1 union W2 is a basis if it is if it spans. So continue the argument, in not more than n minus m equal to k steps, we get a set Sk equal to S union W1, W2, etc. Wk, which is a basis for V. So the theorem says that any linearly independent set can be extended to a basis and any spanning set can be reduced to a basis. So final theorem we are dealing in this section is this. Let W be a subspace of a finite dimensional vector space. Then W is finite dimensional, dimension of W is less than or equal to dimension of V, and W equal to V if and only if dimension of W equal to dimension of V. So for any finite dimensional vector space, the dimension of any subset is either, any subspace is either less than or equal to dimension of V. And if it is equal to dimension of V, then W is V itself. So suppose dimension of E is finite, then it has a finite basis. Okay, then any linearly independent set in V cannot contain more than n elements. Okay, W is a subset, okay, of V, and any basis for W is a linearly independent set of vectors in W which is in V. Therefore, it cannot contain more than n elements. Therefore, we have both A and B. W is finite dimensional, which is less than dimension of V. And for part C, suppose W equal to V, then dimension of W equal to dimension of V. And conversely, if dimension of W equal to dimension of V, then the basis for B, basis B of W is linearly independent subset of V with the dimension of V equal to n. Okay, with the dimension of V equal to n elements. And thus B is a basis because the basis B spans W, okay, and span of B is equal to V. Okay, therefore W equal to V. And we will discuss certain problems. Find a basis for the solution space of this given set of homogeneous equations. So this system, solving the system in any of the methods. So I have reduced it through matrix transformation. So we have the elementary, the echelon form. So we have 2 zero rows, which means there are 2 free variables. So the dimension is the number of equations, the number of unknowns, minus the number of free variables. Not the number of equations, number of unknowns minus number of free variables, that is 4 minus 2. Okay, so solving this, we have x, y, z, w equal to z minus 5 by 3 w, z minus 4 by 3 w, z and w. But z and w are free variables. So we have x, y, z, w equal to some r into 1, 1, 1, 0 and 1 by 3 s into 5, 4, 0 minus 3. Therefore, 1, 1, 1, 0 and 5, 4, 0, 3, 0 minus 3 spans the solution space. Also, we can prove that these two vectors are linearly independent and therefore they form a basis for the solution space of the given system. Next, determine the subspaces of R3 with the dimension 0, 1, 2 and 3. We know that any subspace of dimension 0 is the 0 subspace. So, singleton 0, 0, 0 is the subspace of R3 of dimension 0. Then dimension 1 is the subspace spanned by a single vector which is different from 0. So, you choose a non-zero vector x, y, z, and the span of the set alpha into x, y, z is the subspace of dimension 1. So you can observe that these are the lines passing through the origin and the point x, y, z. Then of dimension 2, you choose 2 non-zero vectors which are linearly independent and spans W2. Okay, so we observe that these are planes passing through the origin and passing through the points x1, y1, z1 and x2, y2, z2. And by the previous theorem, any subspace of dimension 3 is R3 itself. As a third problem, find a basis for the subspace ABCD where C is A minus B and D equal to A plus B of R4. What is its dimension? It's clear that C and D depends on A and B. So if A and B are not related, then the basis will be of 2 elements. So if you choose A, B, C, D, it can be expressed as A into 1, 0, 1, 1 plus B into 0, 1, minus 1, 1 in W. Therefore, these two vectors spans W and these two being linearly independent is a basis for W. Then another problem is using the plus or minus theorem, prove that the polynomials 1 minus x square, 2 minus x square and x cube are linearly independent. Okay. P1 and P2 are of the same degree. So if P1 and P2 may be expressed as a linear combination of the other, and since P1 and P2 are of degree 2, P3 cannot be expressed as a linear combination of P1 and P2. Okay, now degree of P3 is 3 and hence it cannot be expressed as a linear combination of P1 and P2. So since P1 and P2 are of the same degree, we will by using the Wronskian we can see that they are linearly independent. You can choose all the three vectors and see that their Wronskian is not identically 0 and therefore they are linearly independent, but we have to use the plus or minus theorem here. So P1, P2 are linearly independent. There you can use the Wronskian, and being linearly independent and which cannot and the third vector P3 cannot be expressed as a linear combination of these two. So so that means this P3 is outside the span of P1 and P2. Therefore, joining P1 and P2 to the span of them, I mean joining P3 to the span of P1 and P2, we get a linearly independent set. Therefore, P1, P2, P3 are linearly independent. Now, the fifth problem is, in the vector space R4, we have two subspaces A and B. A equal to the span of 1, 2, 0, 1, minus 1, 1, 1, 1, and B equal to span of 0, 0, 1, 1 and 2, 2, 2, 2. Determine A intersection B and compute its dimension. So we already know that the intersection of two subspaces is a subspace. Therefore, A intersection B is a subspace and dimension makes sense then. So let us consider a vector in A intersection B, say X, then it is both in A and B, and both A and B are spans of two vectors. So X is, if it is in A, then X is alpha into 1, 2, 0, 1 plus beta into minus 1, 1, 1. And X in B implies X is equal to some gamma into 0, 0, 1, 1 plus delta into 2, 2, 2, 2. But both are the expressions for X. So therefore, these two are equal. So we will get a system of homogeneous system of 4 equations. Solving them, we get all the coefficients are zeros. Therefore, X is 0. That means A intersection B is the 0 subspace and hence its dimension is 0. Another problem, consider 2x, x minus x square, x plus x square, which is a subset of P2. As a subset of P2, find the dimension of span of S. So noting this, we can see that there is a constant which is of degree 0. There is x of degree 1 and the others, and there is an x square. Others are combinations of x and x square. So this set itself is spanned by 1x and x square. Therefore, span of S is span of 1x x square whose dimension is 3. But we will explore it. So this S is the set of 4 polynomials in P2. So span of S is again polynomials of degree less than or equal to 2. So let us choose a P of x in span of S. So it can be written as 2a into 1 plus b plus c plus d into x plus d minus c into x square. So it belongs to span of 1x x square. Therefore, the span of S is equal to span of 1x x square, which are linearly independent and therefore is a basis and hence dimension is 3. Now, let U equal to set x1, x2, x3 in R3 with 2x1 minus 3x2 plus 5x3 equal to 0 and W equal to x1, x2, x3 in R3 with 4x1 plus x2 minus 3x3 equal to 0. Find dimension of U, W and U intersection W. So let us choose U in U, a vector in U. then it is expressed as a linear combination of the vectors 3 by 2, 1, 0, minus 5 by 2, 0, 1. Therefore, these two vectors spans U, and these two are linearly independent as shown below, and is a basis. Therefore, dimension of U is 2. Similarly, W is spanned by 1, minus 4, 0, and 0, 3, 1, which are linearly independent, and therefore dimension of W equal to 2. Now, choosing a vector in U intersection V, it should be in both U and W. I mean, U intersection W, it is in both U and W. And as proceeds, if you proceed as in the previous problem, you get two equations. Solving them, we have x2 equal to 13 by 2 x1 and x3 equal to 7 by 2 x1. So x2 and x3 are dependent on x1. So there will be just a single vector which is linearly independent, or it is spanned by a single vector. So if you write x as x1, x2, x3, then it is spanned by 1, 13 by 2 and 7 by 2, that particular vector. Therefore, it spans U intersection W, and it being non-zero, it is linearly independent and is a basis. Therefore, its dimension is 1. Another problem is, for each I equal to 1 to n, let ai equal to the n tuple ai1, ai2, etc., ain in Rn. Then the set a1, a2, etc., an is a basis for Rn if and only if the matrix A formed by aij n by n is invertible. To prove that a1, a2, etc., n is a basis, it is enough to prove that every vector in Rn can be expressed as a linear combination of these vectors in a unique way. So let us consider a vector in Rn, and let us choose a linear combination which is equal to x. So k1 a1 plus etc. plus kn an equal to x. So expanding this, we get a system of linear equations, exactly a system of n linear equations in n unknowns. So in matrix form, we have a11, a21, etc., an1, etc., a1n, a2n, etc., ann into k1, k2, etc., kn equal to x1, x2, etc., xn. That is A transpose k1, k2, etc., kn equal to x1, x2, etc., xn, where A transpose is the transpose of A, which is equal to aij n by n. Thus, any x belongs to Rn is a unique linear combination of a1, a2, etc., an if and only if this matrix has this matrix equation has a unique solution. Otherwise, it has different representations. So the equation has a unique unique solution if and only if the corresponding coefficient matrix is invertible. That is, if and only if A transpose is invertible, which in turn implies A is invertible. And that is the proof of the problem.